Tonight, we're going to explore a region of the universe so vast, so empty, and so unsettling that astronomers have struggled for over 40 years to explain how it could possibly exist. Hidden in the direction of the constellation Boötes, the herdsman, lies a hole in the cosmos. Not a black hole, not a dark patch of dust. A genuine emptiness on a scale so absurd that when scientists first stumbled across it, they assumed they had made a mistake. They hadn't. The Boötes Void is a roughly spherical region of space, approximately 330 million light-years across. A bubble of nothing wider than thousands of galaxies, stacked end to end. By every prediction of cosmological theory, that volume should contain around 10,000 galaxies of various sizes. But when astronomers look there, they find roughly 60. 60 galaxies scattered across a region so enormous that light leaving one end takes hundreds of millions of years to reach the other. The rest is silence, the rest is missing, and nobody knows why. By the end of tonight, you're going to understand why this single region of space terrifies cosmologists more than almost anything else in the observable universe. You're going to learn how it was found, what makes it impossible according to our current models of cosmic structure, why the galaxies inside it appear to be arranged in a deeply suspicious pattern, and why some scientists have begun whispering ideas they would never have suggested out loud a decade ago. Ideas involving exotic physics, vanished structures, and possibly even the fingerprints of something that came before our universe began. Before we go any deeper, if you love unraveling cosmic mysteries with us, take a moment to like this video and subscribe to the channel. It's a small action that helps these stories find more curious minds. Now, let's begin where every great mystery begins, with the assumption that the universe makes sense. For most of human history, people looked up at the night sky and saw chaos. Stars scattered seemingly at random, patches of darkness in between them that meant nothing at all. The darkness was just darkness, the absence of stars, empty sky. That changed in the 20th century. When astronomers built more powerful telescopes, they discovered that the dark patches between stars were not empty. They were filled with galaxies, billions and billions of them. The deeper they looked, the more galaxies they found. The Hubble Space Telescope famously stared into a piece of sky no larger than a grain of sand held at arm's length and found 3,000 galaxies waiting there. Wherever astronomers pointed their instruments, the universe revealed itself to be staggeringly full of structure. So when, in the 1980s, a team of astronomers began the painstaking work of mapping galaxies in 3 dimensions, they were certain of one thing. Wherever they looked, they would find galaxies. The only question was how many. What they actually found broke their assumption to pieces. The team was led by Robert Kirshner, then a young astronomer working with 3 colleagues. Their goal was straightforward: measure the distances and positions of as many galaxies as possible in a specific patch of sky and assemble a 3-dimensional picture of how galaxies are distributed in our cosmic neighborhood. They were not searching for anything strange. They were doing the equivalent of a cosmic census, counting houses on a quiet street. But when they finished their calculations and plotted the galaxies on a 3-dimensional chart, they discovered a hole, not a region with fewer galaxies than expected, not a slightly underdense patch, a genuine, gaping absence, a nearly spherical region in the direction of Boötes where the galaxies they expected to find were simply not there. At first, they assumed it was an error. Maybe their distance measurements were wrong. Maybe they had missed a slice of the sky. Maybe their statistical methods were biased. They went back to the data again and again. The void refused to disappear. When they finally published their findings, the response was disbelief. Some astronomers refused to accept the result. Others suggested it must be an artifact of how the survey had been done. But over the following years, as more sensitive surveys were completed and more powerful telescopes peered into that direction, the void only became clearer. It was real, it was enormous, and it was almost completely empty. The numbers tell you why this matters. A region the size of the Boötes Void, located in a typical part of the universe, should contain approximately 10,000 galaxies. Galaxies of every kind: tiny dwarfs, massive spirals, glowing ellipticals. Pairs colliding and merging in slow-motion gravitational dances. The cosmic web, that great filamentary structure that organizes the universe, should be threading through that volume in dense ribbons of light and matter. Instead, only about 60 galaxies have been found inside it. To put that in human terms, imagine driving through a vast metropolitan area where there should be 10,000 houses scattered across the suburbs, the downtown, and the surrounding neighborhoods. And instead, you drive for hundreds of miles in every direction and pass only 60 homes. Most of the lights are out. Most of the streets are missing. The infrastructure of an entire civilization has somehow vanished, leaving behind only a handful of isolated buildings in the dark. That is the Boötes Void. And here is what makes it so much stranger than the other voids astronomers have catalogued. The universe has voids. We know this. Voids are a normal feature of cosmic structure. The matter in the universe is not spread evenly. It clumps along filaments. It pools in clusters. And the spaces between filaments are voids of various sizes. This is expected. But the Boötes Void is in a category of its own. It is not just any void. It is exceptionally large, exceptionally empty, and exceptionally well-defined. Its boundaries are sharper than they should be. Its emptiness is more profound than it should be. And the 60 galaxies that do exist inside it are arranged in a pattern that some astronomers find deeply unsettling. This is the central mystery we're going to explore tonight. How did this hole in the cosmos form? Why is it so much emptier than any model predicts? Why are the galaxies inside it arranged the way they are? And what does the existence of the Boötes Void tell us about the history of the universe, the nature of dark matter and dark energy, and the possibility that there are forces shaping the cosmos we have not yet discovered? Because the universe should not contain a region this empty. Not by accident, not by any combination of known physics. And yet there it is, sitting in the constellation of the herdsman, waiting for us to understand it. A silence so vast that the light from one edge takes longer to cross than the entire age of complex life on Earth. The Boötes Void is not just a hole in space. It might be a hole in our understanding of reality. And tonight, we're going to walk straight into it. To understand why the Boötes Void shook the astronomical community so badly, you have to understand the strange, almost desperate period of cosmic cartography that preceded its discovery. The 1970s and early 1980s were a time when astronomers were doing something nobody had ever truly attempted before. They were trying to map the universe in 3 dimensions, not just where galaxies appeared on the sky, but how far away they were, their depth, their place in the cosmic landscape. This sounds simple. It was not. For most of the 20th century, astronomy had been a 2-dimensional science. When you look at a photograph of the night sky, you see a flat image. A galaxy that appears next to another galaxy in your photograph might actually be billions of light years closer or farther away. You can't tell. The sky compresses everything onto a single plane, and that flatness hides the universe's true shape. To pierce that flatness, astronomers had to measure distances. And to measure distances at cosmic scales, they needed redshifts. The light from a galaxy moving away from us is stretched to longer, redder wavelengths. By measuring how much that light has been stretched, you can calculate how fast the galaxy is receding. And because of Hubble's law, recession velocity is directly proportional to distance. Measure the redshift, calculate the distance, plot the galaxy in 3 dimensions, repeat thousands of times. That was the plan. The problem was that measuring redshifts was painfully slow. Each galaxy required hours of telescope time. You had to focus a spectrograph on its faint light, capture enough photons to identify specific spectral lines, then carefully calculate how far those lines had been shifted from their laboratory positions. In the 1970s, you could measure maybe 1 galaxy per night on a large telescope under ideal conditions. To map a meaningful volume of the universe, you needed thousands of galaxies, tens of thousands. The project would take decades, but astronomers were obsessed. Because the question they were trying to answer was one of the deepest in science. How is matter distributed across the universe? Are galaxies arranged randomly, like grains of sand spilled across a beach? Are they clustered in groups separated by empty regions? Is there a pattern to it all, some grand cosmic architecture invisible from our small vantage point on Earth? Theoretical predictions had been made. Most cosmologists in the early 1980s expected a fairly smooth distribution of galaxies with mild clustering. Some clumps, some thinner regions, but nothing too dramatic. A relatively gentle cosmic landscape, like rolling hills. The universe was thought to be statistically uniform on large scales, with structure only appearing at the scale of individual galaxies and small galaxy groups. This expectation was rooted in something called the cosmological principle. The idea that the universe should look the same on the largest scales, no matter where you stand. That principle had been a cornerstone of cosmology for decades. It was beautiful. It was elegant. It was about to be challenged in ways nobody anticipated. Robert Kirshner was one of the astronomers willing to do the painstaking work. Born in 1949, he had completed his PhD at Caltech and was working at the University of Michigan during the late 1970s. He partnered with 3 other astronomers for the redshift survey that would change everything. Augustus Oemler at Yale, Paul Schechter, who would later become known for his fundamental work on galaxy luminosity functions, and Stephen Shectman, a sharp-eyed observer with deep experience at the great telescopes of the American Southwest. The team's project was modest by modern standards. They were going to measure redshifts for galaxies in 3 thin slices of the sky. 3 narrow strips, like ribbons stretching outward from Earth. The goal was to see how galaxies were distributed along these strips, all the way out to distances of several 100 million light-years. 3 narrow probes into the cosmic depths. They used the 4-meter Mayall telescope at Kitt Peak National Observatory in Arizona, a massive instrument perched on a mountaintop in the Sonoran Desert. Night after night, they pointed it at faint smudges of light. Galaxies so distant that their photons had been traveling for hundreds of millions of years before arriving at the telescope. They captured spectra, measured redshifts, calculated distances, plotted the results. The first 2 slices showed roughly what they expected. Galaxies clustered in groups, some empty patches, nothing dramatic. The data was consistent with mild cosmic clustering. Their colleagues nodded. The work was solid. The universe seemed reasonably behaved. Then they processed the 3rd slice, the one that happened to pass through the constellation Boötes. The data initially looked fine. Galaxies at various distances, a normal-looking distribution near the edges of the slice. But as they zoomed in on a particular range of distances, something appeared on the chart that none of them had ever seen before. A region completely empty of galaxies, not sparse, not underpopulated, empty. A hole in the data, exactly where the cosmological principle said there shouldn't be one. Kirshner has described in interviews how he kept rechecking the numbers. The team examined their telescope logs, the weather conditions during their observing nights, the calibration of their spectrograph. They considered whether they had simply missed a piece of the sky. They considered whether some technical glitch had erased a population of galaxies from their data. They went back to the photographic plates and re-examined every measurement. The void was real. When they finally published the result in 1981 in the Astrophysical Journal, the paper landed in the astronomical community like a stone dropped into still water. The ripples spread outward immediately. Conferences hosted heated debates. Some astronomers argued that a region as empty as the Boötes Void simply could not exist within the framework of the cosmological principle. Others suggested the survey had been biased somehow. Maybe galaxies in that direction were obscured by gas or dust. Maybe the redshift measurements had been contaminated by foreground objects. Kirshner's team defended their work, but they were cautious. They acknowledged that more data was needed. Other teams set out to verify or refute the discovery using independent surveys, different instruments, different techniques. The verification came over the following years from a much larger project. The Center for Astrophysics Redshift Survey, led by Margaret Geller and John Huckler at Harvard, would eventually measure redshifts for tens of thousands of galaxies. When their first slice of the survey was published in 1986, it revealed something nobody had imagined. The universe was not smoothly distributed at all. Galaxies were arranged in vast filaments and walls, separated by enormous voids. The cosmic web, as it came to be called, was the actual large-scale structure of the universe. The Boötes Void had been the first hint, the first sign that the cosmological principle was more subtle than anyone had realized. Yes, the universe is statistically uniform on the very largest scales, but within that uniformity It is sculpted into intricate patterns of density and emptiness, threads of galaxies stretching across hundreds of millions of light years. Walls thousands of galaxies thick, and voids, yawning, gaping voids that take up most of the volume of space. But even within this newly discovered web of structure, the Boötes Void stood apart. Other voids were found, many of them, but none of them were quite like Boötes. None of them were so deep, so sharply defined, so defiantly empty. The discovery had opened a door. But what lay behind that door was about to become something far stranger than anyone in 1981 could have predicted. To grasp why the Boötes Void is so disturbing to cosmologists, you have to understand what they believed the universe should look like before discoveries like this one began complicating the story. And the framework they trusted, the framework that still underlies almost every prediction in modern cosmology, is something called the Lambda Cold Dark Matter Model. Lambda-CDM for short. It is the closest thing science has to a working blueprint of the cosmos. In the Lambda-CDM model, the universe begins in an extraordinarily uniform state. After the Big Bang and the period of inflation that followed it, every region of space looks almost exactly like every other region. The temperature is nearly identical everywhere. The density is nearly identical everywhere. The variations are so small they are almost invisible. About 1 part in 100,000. That is the level of unevenness that existed in the infant universe. That number matters more than almost any other number in cosmology. 1 part in 100,000. If the variations had been larger, gravity would have been too aggressive, and the universe would have collapsed into a chaos of black holes before stars could form. If the variations had been smaller, gravity would have been too weak to pull anything together at all, and the universe would have remained a uniform fog of gas forever. 1 part in 100,000 is the narrow setting that allows structure to exist without being torn apart or never forming in the first place. From that whisper of unevenness, everything we see today was supposed to grow. Slightly denser regions had slightly stronger gravity. They pulled in nearby matter, which made them denser still. Slightly less dense regions lost matter to their neighbors, becoming emptier. Over hundreds of millions of years, this amplification process turned faint quantum fluctuations into the cosmic web. Galaxies condensed in the densest knots. Filaments stretched between them. Voids opened in the underdense regions, slowly inflating as matter drained out of them and into surrounding structures. This was the picture cosmologists held in their minds. A universe sculpted gradually and predictably by gravity, working on a foundation of tiny primordial fluctuations. And because the fluctuations had specific statistical properties, the resulting structures should also have specific statistical properties. Cosmologists could calculate, with confidence, how big the largest expected structures should be, how big the largest expected voids should be, how rare deviations from the norm should be at any given size. This is the part that makes the Boötes Void so unsettling. The mathematics of cosmic structure formation predicts a distribution of void sizes. Most voids in the universe should be relatively modest, somewhere between 30 and 100 million light-years across. These are the voids astronomers find everywhere they look. The cosmic web is honeycombed with them. They are normal, expected, a perfectly natural consequence of gravity slowly pulling matter into filaments while leaving the spaces between filaments to expand. Larger voids should be progressively rarer. Voids of 150 million light-years across should exist, but only a handful per observable universe. Voids of 200 million light-years should be exceptionally unusual, and voids approaching 300 million light-years across, the size of the Boötes Void, should be so rare that finding one in the volume of the universe we can observe is statistically improbable. Not impossible, but unlikely enough that astronomers should not stumble across one in a casual survey of 3 narrow ribbons of sky. Yet there it sits. To make matters worse, cosmologists are not relying on hand-waving arguments here. They have built some of the most ambitious computational projects in the history of science to test their predictions. Programs like the Millennium Simulation, run on supercomputers in Germany in the mid-2000s, modeled the gravitational evolution of more than 10 billion virtual particles, representing dark matter and ordinary matter across a cube of simulated universe. The simulation started with the same kind of tiny density fluctuations that the cosmic microwave background tells us existed in the real early universe. Then it let gravity do its work for the equivalent of 13 billion years. When the simulation finished, the resulting structure looked beautifully familiar. Filaments, clusters, walls, and voids, the cosmic web in all its intricacy. Astronomers compared the simulated universe to the real universe, and on most measures, the match was extraordinary. The Lambda-CDM model was doing its job. It was reproducing the cosmic landscape with stunning accuracy. But when astronomers looked at the void statistics in the simulation and compared them to the real universe, they found a problem. Voids the size of the Boötes Void did appear in the simulations, but only occasionally. And when they did appear, they were never quite as empty as Boötes seems to be. The simulated voids contained more residual galaxies, more wisps of structure. They were softer at their edges, less defined, less complete in their emptiness. The Boötes Void looks sharper than the simulations want it to look. It looks emptier than the math wants it to be. It is the kind of structure that should exist at the very tail of the probability distribution, the kind of thing you might find once in a survey of an enormous volume, not the kind of thing that turns up in a modest 1980s redshift slice of 3 thin ribbons of sky. Some cosmologists have tried to argue that the void is simply a statistical fluke, a rare draw from the cosmic deck of cards. The universe is enormous after all. Improbable things must happen somewhere. Maybe we just happen to find the one outlier void in our cosmic neighborhood. But the more astronomers have refined their measurements over the past 4 decades, the harder this argument has become to sustain. The void is not slightly larger than expected. It is dramatically larger. It is not slightly emptier than expected. It is profoundly emptier. The probability of finding a structure this extreme in the volume we have surveyed keeps shrinking as the data sharpens. By some estimates, the chance of a Boötes-sized, Boötes-empty void existing in the local universe by accident is on the order of 1 in 100,000 or worse. Not impossible, but low enough to make cosmologists deeply uncomfortable. There is also the question of where else such voids might be. If the universe is truly capable of producing structures like Boötes through ordinary gravitational evolution, we should be finding similar voids in other directions. We have found some large voids: the Eridanus supervoid, the local void, the giant void in Capricornus. They are all impressive in their own right, but none of them combines the size, the depth of emptiness, and the sharp definition of Boötes in quite the same way. Boötes is not just an outlier, it is the outlier. This is the conventional wisdom the Boötes Void crashed into. A confident, mathematically grounded picture of cosmic structure that predicted exactly what kinds of voids should exist and how rare they should be. The model worked beautifully for everything else: for the cosmic microwave background, for galaxy clustering, for the distribution of dark matter, for the abundance of galaxy clusters. But on this one point, the universe seems to have left a deeply suspicious thumbprint on the data, and the thumbprint is starting to look less like an accident and more like a clue. The astronomers who first heard about the Boötes Void in 1981 mostly assumed it would dissolve. Not the void itself, but the mystery around it. They expected that as better instruments came online, as more sensitive surveys probed the same region, the apparent emptiness would slowly fill in with galaxies that the original survey had simply missed. This is what usually happens with anomalous results in astronomy. A telescope captures something strange. A better telescope reveals the strangeness was an artifact. The universe returns to its expected behavior. That is not what happened with Boötes. Throughout the late 1980s and into the 1990s, multiple teams of astronomers turned their attention to the void with one explicit goal in mind: find the missing galaxies. Surely they were there, hiding behind dust, dimmed by some cosmic effect, or simply too faint to have been picked up by the relatively modest equipment of the original survey. If you searched carefully enough, with sensitive enough instruments, you would discover that the void was not really empty. It was just inconveniently dim. Greg Aldering and his colleagues at the University of Michigan took on this challenge directly. They examined the region using improved photographic plates and more sensitive spectrographs. They cross-referenced multiple wavelengths. They looked for galaxies that might have been missed because they were unusually faint, unusually small, or unusually distant within the void's volume. Other teams, including Jack Sulentic and his collaborators, ran parallel searches. The community was determined to either confirm the void or eliminate it. What they found, slowly and uncomfortably, was that the void persisted. It did not dissolve. It did not fill in. Each new search uncovered a few more galaxies, but never enough to change the fundamental picture. Searches in the 1980s and early 1990s gradually raised the count from the original handful to something like 60. That number then stabilized. No matter how carefully astronomers looked, the count refused to climb significantly higher. But the truly disturbing discovery was not about the galaxies that were missing. It was about the galaxies that were actually there. When astronomers plotted the positions of those 60 galaxies inside the void, they noticed something that should not have been possible if the void had formed through ordinary gravitational evolution. The galaxies were not scattered randomly through the void's volume. They were not clumped in a single small group. They appeared to be arranged in a kind of tube-like structure cutting through the interior of the void. A thin filament of galaxies threading across the emptiness like a wire stretched through a balloon. This was deeply strange. In the standard model of cosmic structure, voids should not contain coherent filaments inside them. Voids should be where the cosmic web does not exist. The filaments should be on the outside, bounding the void's edges. Finding a filament running through the interior was like discovering an underground river beneath what was supposed to be a perfectly dry desert. The geometry made no sense. Some astronomers speculated that the apparent filament might be an illusion produced by small number statistics. When you have only 60 data points scattered across an enormous volume, you can sometimes see patterns that are not really there. The human eye is famously good at finding shapes in random data. Maybe the filament was an example of cosmic pareidolia, the faces in the clouds of cosmology, but more careful statistical analyses kept finding the same pattern. The galaxies inside the Boötes Void were not arranged randomly. There was structure inside the emptiness, something organized. Something that demanded an explanation as much as the emptiness itself. The next major shift in the story came in the early 2000s, when the Sloan Digital Sky Survey began producing the most detailed three-dimensional maps of the local universe ever made. Sloan was a different kind of project. It used a dedicated 2.5-meter telescope at Apache Point Observatory in New Mexico, optimized specifically for surveying enormous numbers of galaxies. Where Kirshner's original team had measured a few hundred galaxies in 3 narrow ribbons of sky, Sloan would eventually measure redshifts for more than 2 million galaxies, covering a huge fraction of the visible sky. When the Boötes Void was finally mapped with Sloan-quality data, the result was unambiguous. The void was exactly where Kirshner had said it was. It was almost exactly as empty as he had claimed. Its boundaries were almost exactly as sharp. 40 years of follow-up observation had not softened the picture. It had hardened it. This was the moment when the comfortable explanation began to fail. Throughout the 1980s and 1990s, cosmologists could console themselves with the idea that the void was probably a statistical anomaly, a rare draw from a long tail of cosmic probability, improbable but tolerable. With Sloan-era data, this story became harder to maintain. The void was simply too clean, too well defined, too empty, and the structure inside it was too organized. Some researchers began calculating just how improbable the void really is, using the precise statistics of the modern Lambda-CDM model. The numbers were uncomfortable. Depending on which assumptions you used, the probability of finding a void with the size and emptiness of Boötes in the volume of space we have surveyed ranged from about 1 in 10,000 to less than 1 in 1 million. These are not impossible odds. The universe is large. Rare events must happen somewhere. But they are odds that should make any honest cosmologist pause, and there was a second problem looming behind the statistics. The Lambda-CDM model is supposed to predict not just the existence of voids, but their character. The simulations were producing voids of various sizes, including occasional large ones. But the simulated voids were almost always softer than Boötes. Their boundaries were fuzzier. Their interiors contained more stragglers. Their galaxies were distributed in less organized ways. The simulations could occasionally produce a void of the right size. They could not seem to produce a void of the right size with the right kind of emptiness and the right kind of interior structure all at once. A few cosmologists started saying out loud what others had been thinking quietly. Maybe the Boötes void is not just a statistical outlier. Maybe it is telling us something fundamental about cosmology that we have been missing. Maybe the Lambda-CDM model, for all its successes, has a blind spot when it comes to extreme structures like this one. Maybe there is physics at work in shaping the cosmic web that our current theory does not capture. This was a heretical thing to suggest. Lambda-CDM had passed test after test. It was, and still is, the gold standard of modern cosmology. To say that the Boötes void might require new physics was to challenge a framework that almost nobody seriously doubted. But the evidence kept piling up, and the comfortable explanations kept eroding, and a small but growing number of researchers began treating the void not as a curiosity, but as a puzzle that might genuinely break the standard model. The first cracks had appeared. The dismissals had stopped working. The void was no longer a problem for tomorrow. It was a problem for now. And the next stage in this story would only come when astronomers finally had the technology to look at the void in ways that had been impossible before. The story of how astronomers came to understand the Boötes void as well as they now do is, in many ways, the story of a quiet technological revolution that transformed astronomy from a craft into something closer to industrial cartography. None of the discoveries we have discussed would have been possible without a long chain of inventions, refinements, and engineering breakthroughs that allowed scientists to move from measuring one galaxy per night to measuring thousands. In the era when Kirshner and his colleagues made their original discovery, redshift measurements were still done largely with photographic plates and single-object spectrographs. You pointed your telescope at one galaxy. You opened the shutter. You collected light for an hour or two. You developed the plate. You measured the position of spectral lines by hand. You calculated the redshift. Then you moved on to the next galaxy. This process was slow, error-prone, and limited by the patience of human observers and the unforgiving demands of dark mountaintops. The first revolution came with the widespread adoption of charge-coupled devices in the 1980s. CCDs are the silicon chips that today sit at the heart of every digital camera and every smartphone. In astronomy, they replaced photographic plates with something dramatically more sensitive. A photographic plate might capture 1 or 2% of the photons hitting it. A CCD could capture 80% or more. The same telescope using a CCD instead of a plate could see fainter objects, gather more data, and produce results far more quickly. Suddenly, the galaxies that had been invisible at the edges of the Boötes void became at least theoretically reachable. The second revolution was multi-object spectroscopy. Instead of measuring one galaxy at a time, astronomers developed instruments that could measure dozens, then hundreds, then thousands of galaxies simultaneously. The trick was to feed the light from many galaxies into a single spectrograph using carefully positioned optical fibers. Each fiber would catch the light from a different galaxy and route it into the spectrograph for analysis. With this technology, a single night of observation could produce as much redshift data as months of work using the old methods. The most dramatic embodiment of this revolution was the Sloan Digital Sky Survey, which formally began its science operations in the year 2000. The Sloan project used a dedicated 2.5-meter telescope at Apache Point Observatory in New Mexico, paired with a custom-built spectrograph capable of measuring 640 galaxies at once. Over the following decades, Sloan and its successor surveys would measure redshifts for several million galaxies, covering roughly a third of the entire sky. The data set was so enormous that, for the first time, statistical questions about cosmic structure could be answered with real rigor instead of educated guessing. Around the same time, an Australian team was running a parallel project called the 2DF Galaxy Redshift Survey. The 2DF, which stands for 2-degree field, used a similar fiber-fed spectrograph on the Anglo-Australian telescope in New South Wales. Together, Sloan and 2DF gave astronomers an unprecedented map of the cosmic web in the local universe, and that map was finally detailed enough to settle long-standing questions about how voids form, how big they get, and what they contain. But mapping is only half the story. The Boötes Void posed a specific challenge that visible light surveys, no matter how sensitive, could not fully address. What if the void contained galaxies hidden behind dust? What if there were unusual populations of objects that did not emit much visible light, but still represented real matter? To answer these questions, astronomers had to look in other parts of the electromagnetic spectrum. The 2-micron all-sky survey, known as 2MASS, scanned the entire sky in infrared wavelengths from 1997 to 2001. Infrared light passes through interstellar dust far more easily than visible light. If there were galaxies in the Boötes Void that had been obscured by dust in their host environments, 2MASS would catch them. It found a handful of additional candidates, nothing remotely sufficient to fill the void. Radio astronomers performed an even more rigorous test by searching for neutral hydrogen gas inside the void. Hydrogen is the fundamental building block of galaxies. Where there is hydrogen, there are at least the raw materials for star formation. Even galaxies that have not yet formed many stars, even galaxies that are so dim in visible light that they are essentially invisible, still emit a characteristic radio signal 21 centimeters from their hydrogen. Surveys using instruments like the Arecibo Observatory in Puerto Rico, before its tragic collapse in 2020, and the Parkes Telescope in Australia, scanned the void's volume for hidden hydrogen. The results sharpened the mystery rather than solving it. There were no large hidden populations of gas-rich, optically dim galaxies waiting to be found inside Boötes. The void was as empty of hydrogen as it was of stars. Whatever was missing in every form astronomers knew how to measure. While observers were perfecting their tools, theorists were building computational laboratories that would let them simulate the universe and compare its behavior to the real cosmos. The Millennium Simulation, the Illustris TNG project, the Eagle simulation, and several others have created enormously detailed virtual universes that begin in the same conditions as the real Big Bang and evolve forward in time according to the known laws of physics. These simulations require some of the most powerful supercomputers ever built. They track billions of virtual particles representing dark matter and ordinary matter through 13 billion years of cosmic evolution. The simulations have been extraordinarily successful at reproducing many features of the real universe. They generate filaments and clusters that look statistically identical to the ones astronomers observe. They produce voids of various sizes. They predict the right number of galaxy clusters, the right kind of galaxy distribution, the right cosmic microwave background patterns. But when researchers go looking for Boötes-like structures inside the simulations, they consistently come up short. The simulations produce big voids. They do not consistently produce a void this big, this empty, and this sharply defined. Specialized algorithms have been developed specifically to identify and characterize voids in both real and simulated data. Programs with names like ZOBOV, VIDI, and Void Finder use clever mathematical techniques to identify regions of low density without making strong prior assumptions about their shapes. These algorithms have catalogued thousands of voids across the local universe. They have produced detailed statistics on void sizes, void emptiness, void shapes, and void evolution. And they have consistently flagged the Boötes Void as one of the most extreme voids known, sitting at the very edge of what the standard model can tolerate. The most recent technological development to enter the story is the Dark Energy Spectroscopic Instrument, or DESI, which began operations in 2021 at Kitt Peak National Observatory. DESI uses an array of 5,000 robotic fiber positioners to capture spectra from thousands of galaxies and quasars simultaneously. It will measure tens of millions of redshifts over its operational lifetime, producing the largest three-dimensional map of the universe ever assembled. Among many other things, DESI is providing the most detailed view of the Boötes Void ever recorded. And what it is showing us is that the void is real, that the void is exceptional, and that the void may be hiding something deeper than anyone imagined. When astronomers finally had the data they needed to truly characterize the Boötes Void, the first major surprise was not about its emptiness. The emptiness had been the headline since 1981. The first real revelation, the one that began to reshape thinking about how this structure could have formed, was about its shape. For decades, the void had been described in casual terms as a sphere, a spherical bubble of nothing roughly 330 million light-years across. This description appeared in textbooks, in popular articles, in talks at scientific conferences. It was convenient, it was easy to visualize, and it was wrong. When astronomers used the redshift catalogs from Sloan and 2DF to reconstruct the void's true three-dimensional geometry, they discovered something far more complex. The Boötes Void is not a sphere. It is something closer to a peanut, or perhaps a string of beads. Or, in the most poetic description offered by one researcher, a region of space that looks like several large bubbles pressed together until their walls dissolved. The void's boundaries, when mapped carefully, show subtle hints of internal divisions, patches of slightly higher density crossing through the interior, regions where the emptiness seems to deepen and then recede before deepening again. The 60 galaxies inside the void are not arranged randomly, nor in a single filament, but along what appears to be the remnants of structure that once divided the void into smaller voids. The tube-like arrangement that astronomers had noticed earlier turned out to be one piece of a more complex pattern, a skeleton of leftover matter clinging to the boundaries between what might once have been distinct cavities. This discovery led to one of the most important hypotheses in the modern study of the Boötes Void, the void merger hypothesis. The idea is elegant. In the early universe, several smaller voids may have formed in this region of space. Each of them was a normal, statistically ordinary void, the kind of structure that the Lambda-CDM model produces without difficulty. Each of them grew over billions of years, draining matter into surrounding filaments as the universe expanded. And then, as they continued to grow, their boundaries touched, their walls thinned. Eventually, the matter that had once separated them was stretched so thin that the voids effectively merged. The result was a single, much larger void that retained faint traces of its origin in the form of internal structure and slightly uneven boundaries. When this hypothesis was first proposed, the response within the cosmology community was something close to relief. Here, finally, was a possible explanation that did not require new physics. The Boötes Void was not a one-in-a-million statistical outlier. It was not a hint of some unknown force shaping the cosmic web. It was simply the result of several normal voids combining into one extraordinary void. The Lambda-CDM model could survive. The Boötes Void could be tamed. This explanation was developed in the late 1990s and refined in the 2000s by a number of researchers, including the Dutch cosmologist Rien van der Weygaert, who has spent much of his career studying the geometry and evolution of cosmic voids. Van der Weygaert and his collaborators showed that void merging is not just possible, but expected. As the universe expands and structure forms, smaller voids are continuously growing, encountering each other and merging into larger ones. The cosmic web is a dynamic system. What looks today like a single enormous void might be the end stage of a long history of mergers. For a while, this seemed to settle the issue. The community moved on. Other puzzles in cosmology took priority. The Boötes Void became, in many textbooks, a slightly awkward but ultimately understood feature of the local universe, an impressive natural cathedral built by ordinary cosmic processes given enough time. But as the data improved through the 2010s, problems with the merger hypothesis began to emerge. The first problem was timing. The Boötes Void is close to us in cosmic terms. The light from its center has traveled only a few 100 million years to reach our telescopes. This means we are seeing the void in a relatively recent state, not as it existed in the distant past. For the merger hypothesis to work, the voids that combine to form it must have done so within the available time. They must have grown large enough to touch, then merged, then erased almost all traces of their internal boundaries within the age of the local universe. When researchers calculated whether this was actually possible given the rates at which voids are known to grow, the numbers were tight. Not impossible, but uncomfortably constrained. The merger had to have happened almost on a schedule, with little room for variation. The second problem was the depth of emptiness. Even if several smaller voids had merged, the resulting structure should still contain residual matter where their boundaries used to be. There should be filaments, walls, perhaps even small galaxy clusters left over from the merger process. The galaxies that had once lived on the outer edges of the original smaller voids should now be sitting somewhere inside the larger merged void as fossils of its history. Some of this is what astronomers see in the form of the tube-like filament running through the interior, but not enough. The void is emptier than the merger hypothesis predicts it should be. The cleanup process that erased the internal boundaries seems to have been more thorough than gravity alone should allow. The third problem was the sharpness of the outer edges. When several voids merge, their combined boundary should be irregular, lumpy, fractal in character. You would expect the merged void to have a knobby, complex outline reflecting the merger history. The Boötes Void does have some asymmetry. It is not a perfect sphere, but its overall boundary is far smoother and far better defined than a chaotic multivoid merger should produce. It looks, in some respects, as though it has been polished. As if some process had worked to smooth out the edges and define the perimeter more precisely than natural gravitational evolution should be able to manage. These problems did not destroy the merger hypothesis. It remains a serious explanation, perhaps the leading explanation, for the void's existence. But it stopped being a comfortable solution. The merger could account for the void's size, but not for the void's emptiness. It could account for the internal filament, but not for the smooth outer boundary. It explained some features while leaving others stubbornly unexplained. This was the first major discovery of the modern era of Boötes Void research. Not that the void exists, not that it is empty, but that its detailed geometry tells a more complicated story than anyone had assumed. The void is not a simple bubble produced by ordinary cosmic evolution. It is a complex object that bears the fingerprints of multiple processes, some of which we understand and some of which we do not. And the reaction within the scientific community was telling. The initial relief at finding a possible explanation gave way to a more cautious mood. Astronomers stopped describing the void as solved. They began describing it as interesting again. They began asking new questions. And the new questions were leading them somewhere even stranger than the merger hypothesis had hinted at, because the geometry was only the first surprise. The next surprise involved something the void was doing to the universe around it. For most of the history of cosmic void research, voids were imagined as passive features, empty stages on which the more interesting drama of galaxies and filaments played out. They were the absence at the heart of the cosmic web, defined entirely by what was missing. Voids did not do anything, they simply were. This view started to break apart in the early 2010s when astronomers began using new techniques to measure something called peculiar velocity. The peculiar velocity of a galaxy is the part of its motion that cannot be explained by the general expansion of the universe. Cosmic expansion carries all galaxies away from each other at a predictable rate, set by distance through Hubble's law. But on top of that smooth expansion, galaxies have their own additional motions driven by gravity. Some galaxies are falling into clusters. Some are being slingshot through neighbor groups. Some are being deflected by nearby concentrations of mass. By carefully measuring the difference between a galaxy's observed motion and the motion predicted by pure cosmic expansion, astronomers can map invisible gravitational currents flowing across the universe. These currents reveal where matter is concentrated, where it is sparse, and where the cosmic landscape is doing work on its inhabitants. When researchers applied these techniques to galaxies in the vicinity of the Boötes Void, they discovered something that quietly overturned the old view of voids as passive features. The galaxies near the void were not stationary relative to the cosmic expansion. They were not falling inward toward the void's empty center. They were doing something else entirely. They were being pushed away. Imagine a region of space where matter is denser than average. That region has more mass, so it has stronger gravity, so it pulls nearby galaxies toward itself. This is intuitive. Now imagine a region of space where matter is sparser than average. That region has less mass than its surroundings, which means it pulls less strongly than the regions around it. From the perspective of a galaxy sitting between an underdense void and a denser filament, gravity is asymmetric. The denser region tugs harder. The void tugs softer. The net effect is that the galaxy is gradually drawn away from the void and toward the filament. This means voids do not need to push anything in any conventional sense. They influence motion simply by the relative weakness of their gravitational pull compared to the structures around them. Matter flows outward from voids the same way water flows downhill, not because the hill is pushing it, but because there is nothing on the hill to hold it in place. When this dynamic was modeled for the Boötes Void specifically, the results were striking. The void appears to be one of the dominant gravitational influences in our local region of the universe. Galaxies hundreds of millions of light-years away from its center are still measurably affected by it. The matter currents flowing through this part of the cosmic neighborhood owe a substantial fraction of their pattern to the simple fact that the Boötes Void is sitting where it is, exerting its absence on everything within reach. A team of researchers led by Yehuda Hoffman, an Israeli cosmologist who has spent decades studying large-scale velocity flows, helped formalize this idea by introducing the concept of a repeller. A repeller is a region of underdensity so significant that it shapes the motion of surrounding galaxies as if it were pushing them away. The most famous example is the dipole repeller, a vast underdense region in another direction of the sky that appears to be partially responsible for the motion of our entire local group of galaxies. The Boötes Void plays a similar role for nearby structures. It is one of the great cosmic engines whose presence, or more accurately whose absence, is driving the slow rearrangement of matter across our local universe. This was the second major revelation. The Boötes Void is not a passive hole. It is an active sculptor. Its emptiness is not just a curiosity to be catalogued. It is a force, in the sense that physicists use the word, capable of moving galaxies, shaping flows, and influencing the cosmic environment for vast distances around it. And there was a second piece of evidence that emerged around the same time, connected to a phenomenon known as the integrated Sachs-Wolf effect. The name is dense, but the idea is straightforward. When a photon of cosmic microwave background light passes through a cosmic void on its way to Earth, something subtle happens. As the photon enters the void, it climbs out of the gravitational well of the surrounding matter into the lower gravity region of the void. This costs the photon a tiny amount of energy. As it exits the void, it falls back into the gravitational well of matter on the far side, gaining that energy back. In a static universe, these two effects would cancel exactly. The photon would emerge with the same energy it had when it entered. But our universe is not static. It is expanding, and the expansion is accelerating because of dark energy. During the time the photon spent inside the void was stretching. The gravitational well on the far side was not quite as deep when the photon exited as the well on the near side had been when it entered. The cancellation is incomplete. The photon emerges with slightly less energy than it had to begin with. This means that any region of sky behind a large cosmic void should appear slightly cooler in the cosmic microwave background than the surrounding sky. The effect is tiny, almost imperceptible in any single measurement. But by stacking together measurements from many voids and comparing them statistically to measurements from regions without voids, cosmologists can detect the signal. When researchers performed this analysis for the Boötes Void specifically, the result confirmed that the void is producing a measurable cooling effect on the cosmic microwave background, light passing through it. The void is not just a feature of the local matter distribution. It is leaving a fingerprint on the oldest light in the universe. This was profoundly important. It meant that the void's influence extends not just to nearby galaxies, but to photons that have been traveling for nearly the entire age of the universe. The void is interacting with everything that passes through it. It is reshaping the cosmic microwave background. It is shifting velocity flows. It is rewriting, in subtle but quantifiable ways, the structure of the universe in its vicinity. And here is where the deeper unease started to set in among cosmologists. If the void is producing this much influence simply by being empty, what kind of process could have created an emptiness this profound in the first place? Ordinary gravitational evolution from small initial fluctuations should not be capable of producing a structure with this much active influence. Either the Lambda-CDM model is underestimating how dramatic cosmic voids can become, or something happened in this particular region of space that gave the Boötes Void an unusual amount of gravitational reach. It was no longer enough to ask why the void is so empty. Astronomers now had to ask why the void is so powerful. And those two questions, when laid side by side, started to point toward a possibility that had been quietly building since the 1980s. A possibility that the standard explanations were missing something, that the void was telling a story we had not yet learned how to read. A pattern was beginning to emerge from the data, and that pattern was about to get stranger. Once astronomers accepted that the Boötes Void was not a passive feature, but an active gravitational influence on its surroundings, attention turned to a question that had been sitting quietly in the background for decades. What about the galaxies inside it? Those 60 stubborn survivors that had refused to be either erased from the data or fully explained by the void's history. If the void was special, were the galaxies that inhabited it also special? A growing body of research throughout the 2000s and 2010s began answering that question, and the answers were strange enough that they added a third major thread to the mystery. Galaxies that live inside large cosmic voids are now known by a specific term in the literature. They are called void galaxies, and the more astronomers studied them, the more obvious it became that they are not just ordinary galaxies that happen to live in unusual neighborhoods. They are systematically different from galaxies in normal cosmic environments. They are different in size, in composition, in age, in star formation history, in shape, and in the patterns of gas and dust they contain. The first thing astronomers noticed was that void galaxies tend to be smaller than average. The handful that exist inside the Boötes Void are mostly dwarf galaxies, with masses 10 or even 100 times smaller than the Milky Way. There are few medium-sized spiral galaxies among them. There are very few large galaxies. There are essentially no giant elliptical galaxies of the kind that dominate the centers of galaxy clusters. This makes sense in one way, since giant galaxies typically form through repeated mergers, and there is almost nothing inside the void for a galaxy to merge with. But the absence of larger galaxies inside the void is so complete that it raises its own questions about how strict the relationship between environment and galaxy size really is. The second thing astronomers noticed was that void galaxies tend to be gas-rich relative to their size. Most galaxies in dense environments have had their reservoirs of cold gas stripped away by interactions with neighbors, by ram pressure from the intracluster medium, or by tidal forces from passing galaxies. Void galaxies, isolated for billions of years from such disturbances, have retained much of their original gas supply. They are like time capsules carrying a much higher proportion of their primordial hydrogen than galaxies elsewhere. This means they should still be capable of forming new stars long into the future, but it also means they are unusually unevolved. The third and most surprising discovery was about the chemical content of void galaxies. The heavy elements that astronomers call metals, meaning everything heavier than helium, are produced inside stars and scattered into space by supernovas. Over the history of the universe, generations of stars have steadily enriched the cosmos with carbon, oxygen, iron, and the other elements that planets and bodies are made from. Most galaxies show a clear chemical history. Their gas is enriched. Their younger stars contain higher concentrations of heavy elements than their older stars. The buildup of metals over cosmic time is one of the cleanest signatures of cosmic evolution available to astronomers. Void galaxies, including those inside the Boötes Void, show much lower metal abundances than galaxies in normal environments. Their gas is more pristine. Their stars contain proportionally fewer heavy elements. This is partly because they have not had access to the chemical exchange that happens when galaxies interact, and partly because their internal star formation has been slower and more sporadic. The result is that void galaxies look chemically younger than galaxies of equivalent age in denser regions. They are old by the clock, but immature by their composition. There is something profoundly unsettling about this picture. It means that the galaxies inside the Boötes Void are not just sparse, but are themselves stunted. They evolved in extreme isolation, missing out on most of the processes that drove galaxy growth and complexity elsewhere in the universe. They are like creatures that grew up alone, never encountering members of their own species, never sharing resources, never participating in the social dynamics that shape ordinary lives. The more astronomers compared the galaxies in the Boötes Void to galaxies elsewhere, the clearer it became that they form a coherent and distinct population. They are not random survivors. They are a category. They share features with each other that they do not share with galaxies in filaments or clusters, and those shared features all point in the same direction. Long isolation, slow evolution, stunted growth, preserved primordial conditions. But then came the deeper realization that lifted this discovery into something larger. The peculiar properties of void galaxies were not unique to Boötes. Other large voids showed the same pattern. The galaxies inside the local void, the Eridanus supervoid, the giant void in Capricornus, all share a family resemblance with the galaxies of the Boötes Void. They're all small, they're all gas-rich, they're all metal-poor, they're all unusually isolated and unusually pristine. The dynamics that shape void galaxies appear to be remarkably consistent across the universe, regardless of which void you examine. This was the third thread in the emerging pattern. The Boötes Void is not a one-off anomaly. It is the most extreme example of a class of cosmic structures that operate by their own rules. Voids are not just empty regions of space. They are environments. They are ecosystems. They produce a specific kind of galaxy through specific processes, and those galaxies bear the marks of their environment as clearly as deep-sea fish bear the marks of their lightless habitat. And once you recognize voids as ecosystems, you start asking different questions about them. Not just how big they are or how empty they are, but what kind of universe they represent. What would cosmology look like if you grew up inside a void instead of on the edge of one? What kind of observers, if any, could arise inside a Boötes-sized region of profound isolation? What does it mean that some galaxies have spent their entire history with no significant neighbors, while others have been buffeted by gravitational interactions for billions of years? The pattern was no longer limited to the void itself. It extended to its contents, its physical influence, its statistical extremity, and now to a coherent picture of what a void really is. The Boötes Void was emerging as the deepest, sharpest, most thoroughly characterized member of a peculiar category of cosmic structures whose properties are still not entirely understood. But the discovery that pulled the pattern together did not come from studying the void's emptiness, or its galaxies, or its influence on surrounding matter. It came from looking at exactly where the 60 galaxies sit relative to each other. And the result was so strange that it sent some researchers back to their data with the uncomfortable suspicion that the void was hiding something deeper than they had realized. Because the galaxies inside the Boötes Void are not just an isolated population. They are arranged in a way that, when examined carefully, looks less like the leftovers of a chaotic merger and more like the survivors of something specific. Something that may have left its own structural signature on the void's interior in patterns no merger hypothesis can fully account for. And that signature was about to become the heart of the entire mystery. When astronomers finally produced high-precision maps of the 60 galaxies inside the Boötes Void, using the combined data from Sloan, 2DF, and several follow-up surveys, they could see something that had been hinted at for decades but never visualized clearly. The galaxies were not scattered randomly through the interior. They were not clumped near the edges. They did not occupy the leftover walls of merged subvoids the way the merger hypothesis predicted. Instead, they were arranged along a single, surprisingly coherent thread of structure passing through the void's center. A spine. That is the term some researchers began using, almost informally at first, when describing this internal arrangement. A spine of galaxies stretching across the void's interior, from one wall to another, threading through what should have been pure emptiness. The spine was not perfectly straight. It curved and twisted slightly along its length. It was thin, in the sense that the galaxies along it were spaced widely apart. But it was unmistakable. Plot the 60 galaxies in 3 dimensions, rotate the data, and the spine emerged again and again, no matter what angle you viewed it from. The first reaction to this discovery was to assume it was an artifact. Maybe the spine was a projection effect, a coincidence of perspective that disappeared when you accounted for measurement uncertainties. Maybe it was a consequence of survey bias, where galaxies along certain lines of sight were easier to detect than others. Maybe it was a statistical coincidence that human eyes were imposing on essentially random data, but the spine refused to dissolve. Statistical tests, run carefully against the null hypothesis of random distribution, kept finding that the arrangement of galaxies inside the void was significantly more organized than chance would predict. The galaxies were correlated with each other along a single axis to a degree that random scattering could not produce. The spine was real, and the question shifted from whether it existed to what it could possibly be. This is where the merger hypothesis began to fail in earnest. The merger explanation predicts that when several smaller voids combine, the leftover matter from their former boundaries should be arranged in sheet-like or wall-like patterns. The remnants should look like a flattened net of debris, marking the places where the original voids used to touch. They should not form a single coherent line stretching through the void's center. A spine of galaxies arranged along a single axis is not what a multivoid merger leaves behind. It is what a different kind of process produces. It is what you find when matter is drawn along a preferred direction by some organizing influence. It is what filaments in the broader cosmic web look like. And filaments are not supposed to exist inside voids. That is, by definition, what makes voids voids. So the question became impossible to avoid. What is a cosmic filament doing in the middle of the largest, emptiest, sharpest void in our local universe? How did matter manage to organize itself into a coherent thread in a region where there was supposedly not enough matter to organize? Several explanations were proposed. None of them worked completely. The first explanation suggested that the spine is the dying remnant of a filament that was once part of a normal cosmic web region. According to this idea, the area now occupied by the Boötes Void was once an ordinary part of the universe, with filaments and walls and clusters distributed in normal proportions. Then, for reasons not entirely clear, the region began emptying out faster than its surroundings. Most of the matter drained into the surrounding cosmic web. But one particularly stubborn filament refused to dissolve and survived as the spine we see today. This explanation has a problem. Filaments do not behave like this. When a region of the cosmic web evacuates, its filaments evacuate too. They thin out, fragment, and ultimately disperse along with the rest of the matter. A surviving spine is not a natural outcome of normal void evolution. The second explanation suggested that the spine formed before the void did, when the universe was much younger and much denser. According to this idea, an unusually dense filament formed in the early universe, and the surrounding regions then evolved into voids around it, leaving the filament intact at the center. This requires a specific sequence of structure formation that is difficult to reproduce in simulations. Filaments and voids generally form together, not in sequence. They are two sides of the same gravitational process. You cannot easily produce one without the other. The third explanation was more speculative. It suggested that the spine reflects the influence of some structure or process operating on scales larger than the void itself. In this view, the spine is not a remnant of normal cosmic structure, but an imprint of something deeper. Perhaps the alignment of the spine with surrounding cosmic features could give a clue. Perhaps the orientation of the galaxies along the spine reveals a tidal field or large-scale flow pattern that has been carving the void's interior for billions of years. This explanation, while still speculative, has gained traction among researchers studying the alignment patterns of voids and filaments across the local universe. The fourth and most uncomfortable explanation, the one that researchers tend to mention quietly rather than in public lectures, is that the spine might reflect a kind of structure that the standard Lambda-CDM model is not equipped to produce naturally. Perhaps there is physics involved in shaping the cosmic web at extreme scales that we have not yet identified. Perhaps the spine is a clue that voids of Boötes-like extremity are governed by processes slightly different from those that shape ordinary voids. This is not a comfortable place for cosmology to find itself, but the data keeps nudging some researchers in that direction. To make matters more interesting, the spine appears to be oriented in a specific way relative to surrounding cosmic structures. The thread of galaxies inside the void is not pointing randomly. Its axis correlates with the alignment of filaments outside the void. There seems to be a relationship between the internal spine and the broader local cosmic web, as if the spine is participating in some larger pattern of orientations rather than existing in isolation. This is the kind of finding that drives cosmologists to recheck their data several times, because it suggests a level of organization that is not supposed to be there. The paradox of the Boötes void, by this point, had become layered. The void is too big. The void is too empty. The void is too sharp at its edges. The void is too active in its gravitational influence. The void contains a coherent internal spine of galaxies that should not exist by the standard explanations. The galaxies inside it form a chemically and morphologically distinct population that hints at unique evolutionary conditions. And the orientation of the void's internal structure may be tied to patterns in the surrounding universe whose origin remains unknown. Each piece could perhaps be explained on its own with enough effort. The combination is harder. Each anomaly that seemed manageable in isolation becomes more troubling when placed alongside the others. The void started to look less like a statistical outlier and more like a structure whose very existence is asking us to consider the possibility that something has been quietly missing from our cosmology. And the deepest discovery of all, the one that would reshape how some researchers think about not just the Boötes void, but the universe itself, was still ahead. The most shocking revelation about the Boötes void did not come from studying the void in isolation. It came from looking at the void in the context of everything else cosmologists had been quietly puzzled about for years. And when researchers finally stepped back and assembled the pieces side by side, what they saw was not a single anomaly. It was a pattern, and the pattern was telling them something they did not want to hear. For decades, cosmologists had been collecting a small but growing list of observations that did not quite fit the standard model. Each one was treated, in its own time, as a curious oddity, a statistical fluctuation, a measurement uncertainty, a mystery to be solved later. Taken individually, none of them seemed to threaten the broader framework of Lambda-CDM. The model was too successful, too well tested, too thoroughly cross-checked to be undone by a few stubborn details. Astronomers focused on the things the model explained brilliantly and treated the oddities as homework problems for the next generation. But the oddities kept accumulating, and the more they accumulated, the harder it became to dismiss them. One of the most famous oddities is something called the cosmic microwave background cold spot. It is a region in the constellation Eridanus where the temperature of the cosmic microwave background is significantly cooler than expected. Even after accounting for the integrated Sachs-Wolf effect from the Eridanus supervoid, the cold spot is colder than it should be. Some researchers have speculated that it could be evidence of something exotic, a collision between our universe and another universe in a multiverse scenario, the imprint of a topological defect from the very early cosmos, the signature of a primordial structure left over from a phase of physics that no longer exists. Mainstream cosmologists rarely embrace these explanations, but the cold spot remains uncomfortably resistant to ordinary interpretations. Another oddity is what researchers half-jokingly call the axis of evil. When the patterns of temperature variations in the cosmic microwave background are decomposed mathematically, certain large-scale features appear to align with each other and with the orientation of our solar system in a way that should be random, but is not. The alignment is statistically improbable. It suggests either a remarkable coincidence or some unknown physical process organizing the largest features of the cosmic background. There is also the hemispherical power asymmetry, where one half of the sky shows slightly more cosmic microwave background variation than the other half. There is the lack of large-scale correlation in the cosmic background, where the standard model predicts there should be more. There is the cluster of unusually massive galaxies discovered in the early universe by the James Webb Space Telescope, which appear to have formed too quickly and too efficiently for Lambda-CDM to comfortably accommodate. And then there is the Hubble tension, perhaps the most serious anomaly in modern cosmology. Measurements of the universe's expansion rate using nearby supernovae give one value. Measurements using the cosmic microwave background give a different value. The two numbers should agree if Lambda-CDM is correct. They do not. The discrepancy has grown sharper over time, not softer, as measurements have improved. It is now considered one of the most pressing crises in cosmology. What does any of this have to do with the Boötes Void? On the surface, nothing. The void is one anomaly. The Hubble tension is another. The cold spot is another. They occur in different parts of the sky, at different scales, using different observational methods. They have no obvious physical relationship. But here is the unsettling possibility that has begun to emerge in cosmology over the past decade. What if these anomalies are not unrelated? What if they are all symptoms of a single deeper problem? What if our universe, or at least the part of it we can observe, is not as ordinary as Lambda-CDM assumes? This idea has a name. It is called the breakdown of the cosmological principle. The cosmological principle is the foundational assumption of modern cosmology. It states that the universe, on sufficiently large scales, looks the same in every direction and from every location. There are no special places. There are no special directions. Statistical uniformity is supposed to dominate at scales above a few 100 million light-years. Without this assumption, the entire mathematical framework of cosmology becomes much harder to apply. With this assumption, the universe becomes tractable and predictable. The Boötes Void, taken on its own, is a strong but not necessarily fatal challenge to this principle. But when you combine it with the other anomalies, a more troubling picture starts to form. We may live in a region of the universe that is not statistically typical. The local cosmos around our galaxy may contain an unusual abundance of large voids. The matter density in our neighborhood may be lower than the cosmic average. The cosmic microwave background may show alignment features that suggest some preferred direction. The expansion rate measured locally may differ from the expansion rate measured globally because our local environment is unusual. Several researchers have explicitly proposed that we live inside or near a so-called local hole or KBC void, named after the astronomers Kirshner, Barger, and Cowie. According to this hypothesis, our entire region of the universe out to roughly 1 billion light-years is significantly less dense than the cosmic average. The Boötes Void is then not an isolated anomaly, but the most extreme example of a regional pattern. We are not living on the cosmic web. We are living in a particularly empty corner of it. If this is true, it would reframe almost everything. The Hubble tension could potentially be explained by the fact that the local expansion rate, measured inside an underdense region, would naturally differ from the global rate. The peculiar velocities of nearby galaxies could be explained by the gravitational influence of surrounding overdense structures, pulling matter outward from our local emptiness. The pattern of voids in our neighborhood could be explained as the natural consequence of living in an unusual region of cosmic structure, and the Boötes Void could be reinterpreted as the dominant feature of our local cosmic environment, not as a freak occurrence. The Boötes Void becomes the keystone, not because of what it is on its own, but because of what its existence implies about everything around it. If the cosmological principle is intact, the void is a 1 in a million statistical curiosity. If the cosmological principle is breaking down in our local universe, the void is exactly what we should expect to find, and its presence helps explain why so many other measurements have been giving us inconsistent answers. This is the reframing that has begun to circulate quietly in the cosmology community. It is not a finished theory. It is not consensus. Plenty of researchers continue to defend Lambda-CDM as the most successful framework we have, and they argue that the anomalies will resolve themselves as measurements improve. But a growing number of voices are willing to consider the alternative, that our cosmic neighborhood is genuinely peculiar, that the universe at the largest scales may not obey the simple symmetries we attributed to it, that the Boötes Void is not just a hole in space, but a hole in our model. If that is true, then everything we think we know about how the universe works, on the very largest scales, may need revision, and the implications go far beyond a single anomalous void. If the Boötes Void is genuinely a keystone in a larger pattern of anomalies, then the consequences for modern science are not modest. They reach into the heart of how we have come to understand the universe over the past century, and they call into question some of the foundational assumptions that almost every major theory in cosmology depends upon. Consider what gets revised if the cosmological principle no longer holds at the scales we observe. Almost every measurement of cosmic distance, cosmic age, and cosmic composition rests on the assumption that we are observing a representative sample of the universe from a typical vantage point. When astronomers calculate the age of the cosmos at 13.8 billion years, they are using a model that assumes the universe behaves the same everywhere on large scales. When they conclude that dark energy makes up roughly 68% of the cosmic energy budget, they are extrapolating from local observations to a global average using equations that assume homogeneity. When they compute the Hubble constant, or the matter density, or the curvature of space, they are leaning on the cosmological principle every step of the way. If the principle breaks down, these numbers do not necessarily become wrong, but they become uncertain in ways they were not uncertain before. We may not be measuring the universe. We may be measuring our particular corner of it, and our corner may be peculiar enough that extrapolating from it to the whole cosmos involves errors that cosmologists have not yet learned to correct. This is the kind of problem that can shake a field. It has happened before in physics. The shift from Newtonian gravity to general relativity in the early 20th century did not erase Newton's equations. It revealed that those equations were a special case of a deeper theory that applied more generally. Similarly, if Lambda-CDM turns out to be a description of our local universe rather than the cosmos as a whole, we may eventually look back on it as a powerful and useful approximation that needed to be embedded in a richer framework. Not wrong, but incomplete in ways we did not previously appreciate. Several alternative or complementary frameworks have been waiting in the wings, gaining attention as the anomalies pile up. The first is a family of approaches known collectively as inhomogeneous cosmology. These models attempt to describe the universe without assuming statistical uniformity at observable scales. Instead, they allow density and expansion rate to vary across the cosmos in ways that depend on local conditions. Some inhomogeneous models can naturally accommodate features like the Boötes Void without requiring rare statistical fluctuations. They can also offer alternative explanations for the apparent acceleration of cosmic expansion, suggesting that what we attribute to dark energy may partly be an artifact of light passing through underdense regions during its journey to us. This idea, known sometimes as the timescape cosmology developed by the New Zealand cosmologist David Wiltshire, has been gaining cautious interest in recent years. It does not eliminate dark energy entirely, but it suggests that the simple Lambda-CDM picture may be over-attributing to dark energy what should partly be attributed to inhomogeneity. The second is modified gravity. The idea here is that the equations describing gravity, given to us by Einstein in 1915, may need adjustments when applied to galactic or larger scales. Modified Newtonian dynamics, or MOND, is the best-known version of this approach. MOND has had some success explaining galaxy rotation curves without invoking dark matter, and various extensions of the theory attempt to address cosmic structure formation as well. If a structure like the Boötes Void cannot be produced by ordinary gravity acting on standard initial conditions, perhaps it can be produced more naturally by a modified gravitational framework. Modified gravity remains a minority view in cosmology, but the persistence of unexplained anomalies has kept it from being dismissed. The third is a class of ideas involving non-Gaussian primordial fluctuations. In the standard inflationary picture, the seeds of all cosmic structure came from quantum fluctuations during inflation, and those fluctuations had specific statistical properties. They were Gaussian, meaning they followed a particular bell-shaped probability distribution. But some inflationary models predict that the actual distribution should have small deviations from Gaussianity. Tiny non-Gaussian features in the initial conditions could amplify into observable consequences over billions of years. A structure like the Boötes Void might be evidence that the universe started with slightly more complicated initial conditions than the simplest inflation models suggest. This would not break cosmology, but it would tell us something important about what happened in the first fraction of a second after the Big Bang. The fourth is the more speculative possibility that primordial black holes played a larger role in cosmic structure than has been appreciated. If significant numbers of black holes formed in the very early universe, before any galaxies existed, they could have acted as gravitational seeds for unusual structures. Some researchers have explored whether primordial black holes might explain anomalies in the cosmic web, including the existence of structures that are too extreme for ordinary gravitational evolution. The Boötes Void could potentially fit into such a framework, particularly if the spine of galaxies inside it traces a primordial gravitational configuration that survived for billions of years, and there are still more exotic ideas in the background. The collision of our universe with another universe in a multiverse scenario, the presence of cosmic strings or other topological defects from the early universe, the influence of physics beyond the standard model leaving observable imprints on cosmic structure. None of these are mainstream, but none of them can be entirely ruled out by current data either. The point is that the anomalies, including the Boötes Void, have created an opening for ideas that would have been laughed out of the room 20 years ago, and that today are taken seriously enough to publish in peer-reviewed journals. There is also a quieter shift happening inside the cosmology community itself. Researchers are beginning to talk about what some have called humble cosmology. The recognition that our knowledge of the universe may be less complete than we thought a decade ago. The acknowledgement that the standard model is a tool, not a final truth. The willingness to entertain alternative explanations for phenomena that previously seemed settled. The Boötes Void has become one of the standard examples cited in these conversations. Not because it has overturned Lambda-CDM by itself, but because it has helped puncture the assumption that everything important in cosmology has already been figured out. If a single void in the constellation of the herdsman can force us to reconsider whether the cosmological principle holds, whether dark energy is what we think it is, whether structure formation operates the way we have modeled it, and whether our local universe is representative of the cosmos as a whole, then the implications go far beyond one anomalous region of sky. The Boötes Void has become a symbol of how much we still do not understand. It is a reminder that the universe is under no obligation to fit our theories. It exists on its own terms, and when its features stop matching our predictions, the proper response is not to dismiss the features, but to question the predictions. What that questioning will ultimately reveal, no one yet knows. But the willingness to ask the questions, prompted in part by the stubborn existence of this single empty region of space, has already begun to change how cosmologists approach their own science. There is a temptation, when reading about cosmic structures hundreds of millions of light years across, to treat them as purely abstract. Numbers, diagrams, concepts that exist in scientific papers but do not really touch ordinary human life. The Boötes Void can seem like one more piece of cosmic trivia. Big, empty, curious, but ultimately something happening far away to nothing in particular. That framing falls apart the moment you try to imagine what it would actually be like to live there. Suppose, for the sake of thought, that a civilization had arisen on a planet orbiting one of the 60 galaxies inside the Boötes Void. Suppose those beings were curious about their universe, as humans are. Suppose they developed astronomy, built telescopes, learned to measure the distances and movements of celestial objects, just as we did. What would their universe look like to them? The first thing they would notice, even with the naked eye, is that their night sky is almost empty. Our night sky is rich. Even from a modestly dark site, you can see thousands of stars without any optical aid. The band of the Milky Way crosses overhead like a luminous river. On a clear winter night in the right latitudes, you can spot the Andromeda Galaxy as a faint smudge, 2.5 million light-years away. The sky feels populated. It feels like a community of lights, even if most of those lights are within our own galaxy. A civilization in the Boötes Void would not have this experience. Their home galaxy would likely be a small dwarf with fewer stars and a less dramatic structure than the Milky Way. The night sky from such a galaxy would have far fewer visible stars overhead, and when they pointed their telescopes outward, hopping to find other galaxies the way we found Andromeda, they would discover that the nearest significant galaxies were not millions, but hundreds of millions of light-years away. To them, the cosmos would appear nearly empty, a vast darkness with their tiny island floating alone at its center. This is not metaphor. This is the actual observational situation faced by any observer inside a large void. Their entire cosmic context would be impoverished compared to ours. Their understanding of cosmic structure would have to be built from a much sparser data set. They would have to work much harder to discover the cosmic web at all, because most of it would be too distant to study in detail. There is a real possibility that an intelligent species growing up in such an environment might conclude that the universe is a fundamentally lonelier and emptier place than humans have come to believe. They might develop entire schools of cosmological thought based on the premise that what they see locally is representative of the cosmos as a whole. They might never discover that filaments of galaxies stretch through the universe like luminous arteries, because the filaments they could observe would be too far away to study with any clarity. And here is the unsettling reversal. They might be wrong, but we might also be wrong in the opposite direction. We grew up in a relatively crowded part of the cosmic web, in the local sheet, with the Andromeda Galaxy close enough to see and dozens of dwarf galaxies in our immediate neighborhood. Our intuitions about how the universe looks are shaped by where we happen to live. If we had grown up inside the Boötes Void, our cosmology might be very different and possibly more accurate in some ways than the cosmology we have developed from our richer vantage point, or possibly less accurate. The point is that location matters, even on cosmic scales. Even what counts as a typical view of the universe depends on whether you live in a populated region or an empty one. This realization is humbling in a way that is hard to articulate. It means that our knowledge of the cosmos, vast and detailed as it is, has been shaped by the accident of our address. We are observers embedded in a specific place. The universe we describe is the universe as seen from that place. We cannot easily step outside ourselves to check whether our perspective is biased. We can only build models and hope that they account for what we cannot directly see. There is a deeper personal resonance to all of this, one that goes beyond scientific accuracy. The Boötes Void offers a stark image of cosmic isolation. Not the metaphorical loneliness of being a single thinking creature in a vast cosmos, but the literal isolation of being separated from the rest of the universe by hundreds of millions of light-years of nothing. The galaxies inside the void are real. The hypothetical civilizations there, if any, would be real, and they would be more alone than we can easily imagine. Most of human emotional life happens at the scale of homes, neighborhoods, cities. We rarely confront the kind of distance that cosmic voids represent. When we look up at the night sky and feel a flicker of awe or unease, we are sensing a fragment of the cosmic scale, and even that fragment is barely tolerable for most people. The Boötes Void, fully grasped, is on a different order of magnitude. It is loneliness on a scale that cannot be felt directly, only thought about. And the act of thinking about it, even briefly, can shift how you feel about your place in the universe. It can also reframe how you feel about your situation here on Earth. We are not in the void. We are in a relatively dense corner of the cosmic web, surrounded by other galaxies that we can study, photograph, and one day, perhaps, communicate with. The light from Andromeda reaches us in a couple million years rather than a couple hundred million. The cosmic environment that produced Earth and humanity is one of the richer environments the universe offers. There are people who treat this as evidence that the universe was made for us. There are people who treat it as evidence that we are simply lucky. There are people who reject both framings and prefer to live without any cosmic narrative at all. But regardless of interpretation, the existence of the Boötes Void puts a finer point on the question. There are places in the universe where complex life, if it exists, would have a much harder time finding meaning in the cosmos. Places where the sky is darker, the neighbors are fewer, and the cosmic context is sparser. We are not in one of those places, whether by design, chance, or simply the statistics of where complex chemistry can flourish. We have ended up in a cosmic environment that is comparatively generous. The Boötes Void reminds us that this generosity is not universal. There is also a more uncomfortable possibility that the void points toward. If our local cosmic environment is unusual, if we live in a region that is denser than most, or more organized than most, then our experience of the universe may be even less representative than we assumed. The cosmos may be far more dominated by voids than by filaments, far more empty than full, far more lonely than connected. The Boötes Void is not the universe's most extreme feature. It is one we happen to be close enough to study. There may be larger, emptier voids beyond our observational reach. There may be regions where cosmic loneliness is the rule rather than the exception. If that is true, then we are not just lucky. We are extraordinarily lucky. And the night sky above us is not just beautiful. It is a privilege most of the universe does not enjoy. Despite 4 decades of careful study, the Boötes Void remains stubbornly unsolved. Each new generation of telescopes has refined our picture without resolving the central mystery. We know more about the void now than we did when Kirshner and his colleagues first announced its existence. But the deeper we look, the more questions accumulate. And the most honest assessment of where we stand today is that the void's basic puzzles are still open, and the tools that may finally answer them are only now beginning to arrive. The most fundamental open question is also, in some ways, the simplest. How did it form? The void merger hypothesis remains the leading conventional explanation, but it does not account for all of the void's features. Alternative explanations involving non-Gaussian initial conditions, primordial seeds, or modified gravity remain on the table, but none of them is supported by enough independent evidence to displace the standard picture. Cosmologists are essentially in a holding pattern. They have a structure they cannot fully explain, several competing explanations that each fall short in different ways, and no clear path forward without more data. The second question is about the void's internal mass distribution. Astronomers have mapped the galaxies inside the Boötes Void with reasonable precision. They have estimated the amount of neutral hydrogen gas. They have searched for dim dwarf galaxies and other normal matter that might be hiding in the emptiness. But the matter we can see is only a fraction of the matter that actually exists. Dark matter dominates the universe's mass budget, outweighing ordinary matter by a factor of about 6 to 1. We know dark matter is there because we can measure its gravitational effects. We do not yet know how it is distributed inside the Boötes Void in fine detail. This matters because dark matter and visible matter generally trace each other. Where there are galaxies, there is usually dark matter. Where there are filaments of galaxies, there are usually filaments of dark matter. The cosmic web is, fundamentally, a dark matter structure with visible galaxies acting as luminous markers of the underlying mass distribution. Inside the Boötes Void, we expect dark matter density to be low. But how low? Could there be hidden dark matter structures inside the void that visible galaxies do not trace? Could the spine of galaxies through the void center be sitting on top of a dark matter filament that we cannot directly detect? Or is the void empty of dark matter as well, in proportions that match the visible emptiness? These are not idle questions. The answer would tell us whether the void's emptiness is a complete absence of mass or simply an absence of normal matter, while dark matter still fills the region in subtle patterns. The two scenarios have very different implications for how the void formed and what kind of physics shaped it. Several upcoming and ongoing observational projects are poised to begin answering these questions. The most powerful new instrument now in operation is the Vera C. Rubin Observatory, a wide-field telescope built on Cerro Pachon in Chile. Rubin will begin its primary survey, called the Legacy Survey of Space and Time, in the mid-2020s. Over 10 years, it will image the entire visible sky every few nights, building up an unprecedented multi-wavelength record of cosmic structure. Rubin will catalogue billions of galaxies, measure their positions with extreme precision, and provide the deepest and most complete map of the cosmic web ever assembled. For the Boötes Void, this means a far more detailed picture of its boundaries, its internal structure, and its galactic population. In space, the European Space Agency's Euclid mission launched in 2023 and is now in operation. Euclid is specifically designed to map the geometry of the dark universe by measuring the shapes of more than 1 billion galaxies and tracking how light is distorted by intervening dark matter. This technique, called weak gravitational lensing, can effectively reveal the distribution of dark matter even when visible matter is sparse. Euclid will be one of the most powerful tools we have for mapping the dark matter content of voids, including the Boötes Void. If hidden dark matter structures exist inside the void, Euclid has a chance of finding them. The Nancy Grace Roman Space Telescope, scheduled for launch later in the decade, will complement Euclid with its own deep, wide-field survey capabilities. Together, these missions are expected to transform our understanding of cosmic structure at large scales. Meanwhile, DAISY continues its primary survey, measuring the redshifts of tens of millions of galaxies. As its data set grows, the statistical confidence in any conclusions about voids, including the Boötes Void, will grow as well. Subtle features that are currently borderline detections will become firm results. The internal spine, the sharp boundaries, the alignment of internal structure with external filaments. All of these will be tested with much higher precision than has previously been possible. Radio astronomy is also approaching a major turning point. The Square Kilometre Array, an enormous international radio observatory under construction in South Africa and Australia, will provide unprecedented sensitivity to neutral hydrogen across the universe. It will be able to map hydrogen in galaxies that are too faint to be detected at optical wavelengths. This will allow astronomers to search for any hidden gas-rich population inside the Boötes Void that previous surveys may have missed. If any unseen galaxies are lurking there, the Square Kilometre Array will likely find them. If it does not, the void's emptiness will be confirmed at a level of confidence that no previous survey could provide. Future cosmic microwave background experiments, including the Simons Observatory in Chile and the planned CMB-S4 project, will also play a role. They will measure the cosmic microwave background with higher precision than ever before, providing tighter constraints on the integrated Sachs-Wolf effect from voids, on the alignment patterns that may or may not exist in the cosmic background, and on the broader question of whether the standard cosmological model fully captures what the universe is doing at the largest scales. Computer simulations are also advancing. Newer generations of cosmological simulations are running with finer resolution, more realistic physics, and larger volumes than ever before. They are starting to produce more rare and extreme structures. The question of whether a Boötes-like void can naturally emerge from Lambda-CDM initial conditions with all of its observed features is one that improved simulations may eventually settle. If the simulations can produce such a structure, the merger hypothesis, or some refined version of it, may turn out to be correct after all. If they consistently fail to produce it, the case for new physics becomes stronger. Underneath all of this lies a question that no telescope can directly answer. We still do not know what dark matter actually is. Direct detection experiments continue to search for weakly interacting massive particles, axions, and other candidates. If dark matter turns out to be something more exotic than current models assume, the implications for void formation could be substantial. The truth is that the Boötes Void may not be fully solved within the lifetimes of the people currently working on it. The pace of cosmic research is patient. The data accumulates over decades. The instruments are built on schedules measured in many years. But the next 10 to 20 years are likely to bring more relevant data than the previous 40 combined. We are entering an era when the void may finally start giving up its secrets, and the question of whether what it tells us will fit comfortably into our existing models or whether it will force us to build entirely new ones remains genuinely open. Step back from the technical questions for a moment and consider what the existence of the Boötes Void actually says about the universe we live in. Not the cosmology of it, not the physics, the bare fact that such a region exists and that we have managed to discover it. The universe, on every scale we have examined, prefers emptiness to fullness. The atom is mostly empty space. The solar system is mostly empty space. The galaxy is mostly empty space. The cosmic web is mostly empty space. The largest structures in nature are not the bright filaments of matter that catch our attention, but the voids between them. Matter is the exception. The void is the rule. Everywhere we look, when we look closely enough, we find that nothing dominates and something is a rare guest. In this context, the Boötes Void is not really an anomaly. It is the universe taken seriously. It is what you get when emptiness is given enough room to express itself without the local interruption of stars and gas and galaxies. The terrifying thing about it is not that such a region exists. It is that the conditions producing such regions are everywhere. The cosmos is not full of things with gaps between them. It is full of gaps with things scattered through them. The Boötes Void simply shows us what one of those gaps looks like when there are almost no things to obscure it. There is something both humbling and liberating in this realization. Humbling because it forces us to acknowledge how small the territory of matter actually is in this universe. We are made of stuff. We live among stuff. We tend to assume that stuff is the basic feature of reality, but the cosmos disagrees. The cosmos seems to prefer nothing and merely tolerates something in specific corners under specific conditions. We are guests in a house whose primary architectural feature is empty space. Liberating because it offers a different way to think about meaning and presence. If matter is the rare and beautiful exception in a universe dominated by void, then the existence of matter, and especially the existence of complex matter capable of awareness, becomes more remarkable rather than less. We are not common features of the universe. We are unusual events. Whatever caused atoms to organize themselves into molecules, and molecules into cells, and cells into bodies, and bodies into minds capable of looking out at the cosmos and wondering about it, did so against the background of an overwhelming preference for nothing. The fact that anything looks back at the void at all is one of the strangest facts in the universe. The Boötes Void invites a particular kind of reflection that humans have engaged in for a long time, sometimes through religion, sometimes through philosophy, sometimes through quiet personal contemplation. The reflection is about what it means to confront emptiness, not metaphorical emptiness, not the emptiness of disappointment or grief or absence in a personal sense. The emptiness of literal nothing, sustained across distances so vast that the human mind cannot truly hold them. When you read that the Boötes Void is 330 million light-years across, your mind does something almost automatic. It produces a brief image, a vague sense of bigness, a feeling that this is impressive. Then it moves on. The number is too large for genuine comprehension. It defeats imagination. You cannot picture 330 million light-years of nothing. You can only know intellectually that it is there, but knowing it intellectually has its own effect. The knowledge sits in the background of your mind like a stone in a pond. It does not need to be present to consciousness to have weight. The fact that such a structure exists changes what you know about reality, even if you cannot directly feel that change. The universe is bigger and emptier and stranger than you previously thought. Once you have learned that, you cannot unlearn it. The information becomes part of you, even if it remains incomprehensible. There is a kind of cosmic perspective that emerges from sustained contact with this kind of information. Astronauts have described something like it after looking down at Earth from orbit. Philosophers have described something like it after long meditation. Scientists have described something like it after spending decades thinking about the universe at large scales. It is not depression. It is not despair. It is not even sadness. It is closer to a quiet recognition that the human scale concerns that dominate our daily lives are not the full picture. There are other scales. There are scales at which entire civilizations would not be visible, much less individual lives. There are scales at which our planet, our solar system, our galaxy are too small to register. This recognition does not have to lead anywhere in particular. It does not have to produce a religious response or a nihilistic one or a stoic one. It does not have to change how you treat the people in your life or how you organize your day. What it does, simply, is widen the frame. It reminds you that the human story is happening inside a much larger story. That story includes the Boötes Void. It includes regions of cosmic emptiness so vast that almost nothing happens inside them. It includes processes that have been unfolding for billions of years and will continue unfolding for trillions more, with or without us. And yet here we are, inside the larger story, aware of it, mapping its features, sending telescopes into orbit, designing experiments to measure photons that traveled for nearly the entire age of the universe before reaching our detectors, doing science. The most extraordinary thing about the Boötes Void may not be the void itself, but the existence of creatures patient and curious enough to find it, to measure it, to argue about how it formed. This is the deeper philosophical resonance of cosmic void research. The voids are vast. The voids are old. The voids will outlast us by stretches of time that make all of human history look momentary. But we have found them. We have given them names. We have begun the slow, careful process of understanding them. That process is unlikely to end in any final answer. It is unlikely to end at all. Cosmology, like life itself, is a story that keeps unfolding, but the unfolding is real. The understanding, however incomplete, is real. The universe contains a region nearly empty enough to count as nothing, and inside another part of that universe, far away from the void, on a small planet orbiting an unremarkable star in an unremarkable galaxy, beings made of matter looked out and noticed. They built tools. They measured. They calculated. They argued with each other about what their observations meant. And eventually, they came to understand that the universe is mostly void, that they are exceptions, that their place in the cosmos is not central, but is nevertheless real, and that the simple act of paying attention to it all is, in some quiet way, the most distinctive thing they do. The Boötes Void will outlast every human concern. It will be there long after every problem you have ever worried about has dissolved into the deep past. And yet for this brief moment, we are here, and we know about it, and we are trying to figure out what it means. That might be the only thing that needs to be said about it. Walk outside tonight on a clear evening in the right season and look up toward the constellation of Boötes. You will recognize it by its bright orange star Arcturus, one of the most familiar stars in the northern sky. The herdsman's kite-shaped pattern stretches above and behind Arcturus, marking out a region that has been part of human mythology for thousands of years. The Greeks saw a herdsman. The Babylonians saw a plowman. Other cultures saw other figures. The pattern of stars was familiar, comforting, fixed in place across generations. What no civilization knew, until just over 40 years ago, is that behind those stars, far beyond the few thousand light years where the constellation's individual suns reside, lies a hole in the cosmos. A region of space so empty that the very concept of emptiness needs new definitions to describe it. A void that should not exist on the scale that it does, that contains structure that should not be there, that influences matter and light for hundreds of millions of light years around it, and that may be a clue to something fundamentally missing from our understanding of how the universe works. The Boötes Void is not just a feature of the sky. It is a question carved into the cosmos, a question we have not finished answering. A question whose answer may eventually require us to rewrite portions of cosmology we currently treat as settled. Think about what we have walked through tonight. A discovery made in 1981 by a young astronomer doing routine survey work, almost dismissed at the time as a mistake. A void that refused to disappear no matter how many telescopes were turned on it. A standard cosmological model that predicted this kind of structure should be so rare that finding one in our neighborhood is statistically uncomfortable. A merger hypothesis that almost saved the standard picture, but ultimately could not fully explain the void's sharpness, depth, and internal organization. A spine of galaxies running through the void's interior, defying every easy explanation for how it could be there. An active gravitational influence that reshapes the motion of matter for vast distances around. A signature in the cosmic microwave background revealing that the void is leaving its fingerprint even on the oldest light in the universe. And then the larger pattern. The realization that the Boötes Void may not be an isolated puzzle, but a piece of something much bigger, a cosmological principle that may not hold at the scales we can observe, a Hubble tension that refuses to resolve, a cold spot in the cosmic microwave background that exceeds simple explanation, anomalies in the early universe galaxies discovered by the James Webb Space Telescope, a growing suspicion that our local cosmic neighborhood may be unusual in ways we have not yet accounted for, and a recognition, slowly spreading through the cosmology community, that our understanding of the universe at the largest scales may be less complete than we believed. All of this from a single empty region in the constellation of the Herdsman. The Boötes Void is, in some sense, a mirror. It reflects back our own assumptions about how the universe should behave. Wherever those assumptions fail to match what we see, the void shows us the gap between our models and reality. We can dismiss those gaps, or we can let them teach us something. The history of science suggests that the gaps are usually the most valuable things we find. They are where the next discoveries hide. They are the openings through which new physics enters the world. We do not know yet what new physics the Boötes Void is pointing toward, if any. We do not know if it will eventually be tamed by improvements to the standard model, or if it will be the wedge that pries open something deeper. We do not know if the next generation of telescopes will find galaxies that have been hiding in its emptiness all along, or if it will turn out to be even more empty than we currently believe. We do not know if the spine of galaxies inside it will be explained by ordinary mergers, or by something far stranger. We do not know if our local cosmic neighborhood is typical or anomalous. We do not know if the cosmological principle holds. We do not know if Lambda-CDM is the final word. What we do know is that the void is real, that its emptiness, whatever its cause, is one of the most striking features of the observable universe, that it is teaching us something about cosmology, about scale, about our place in the cosmos, and about the limits of our knowledge, that we live in an interesting time. A time when the comfortable certainties of late 20th century cosmology are being challenged by new observations. A time when curiosity, properly applied, can still produce genuine surprises. The night sky above you contains thousands of stars you can see and hundreds of billions you cannot. It contains galaxies in every direction. It contains filaments of cosmic structure stretching for distances the human mind cannot encompass. And in the direction of Boötes, beyond the visible stars, beyond even the nearest galaxies, the universe opens into a silence so vast that we are still trying to learn how to listen to it. A silence that began long before humans existed, that will continue long after we are gone, and that will probably outlast every star whose light we see overhead tonight. We have found it. We have measured it. We have named it. We have tried, again and again, to explain it. We have failed again and again to fully account for it, and the silence remains, waiting for us, patient as only cosmic structures can be patient, holding whatever truths it holds in a darkness too deep for our current instruments to fully illuminate. Perhaps the most striking thing about all of this is the simple fact that we know about it at all. Beings made of matter, on a planet orbiting an ordinary star, in an ordinary galaxy, in a relatively crowded corner of the cosmic web, have managed to detect a region of profound emptiness 300 million light-years across and hundreds of millions of light-years away. We have done so with our minds, our instruments, our patience, and our willingness to keep looking at what does not match our expectations. That is no small thing. The Boötes Void may be unsolved, but it is not unseen. And in cosmology, being seen is often the first step toward being understood. If you have stayed with us through this entire exploration, thank you. The journey through cosmic voids, cosmic mysteries, and the limits of what we know is not a quick one. Tonight we have walked together to the edge of an emptiness so vast it bends our understanding, and we have looked into it as far as our current knowledge allows. There is more out there. There is more to discover, more to question, more to be amazed by. If this story moved you, if it stretched your sense of scale, if it left you with questions you want to keep thinking about, take a moment now to like this video, to subscribe to the channel for future deep explorations of the cosmos, and to leave a comment below telling us what part of the Boötes Void mystery struck you most. Was it the void's impossible emptiness? The strange spine of galaxies inside it? The hint that our entire cosmological model may need revision? Share it with us. Share this video with someone who needs to look up at the sky tonight with new eyes, because somewhere out there, in the direction of the herdsman, the silence is waiting. And one day, we may finally understand what it has been trying to tell us. Until then, keep looking up.